Hey guys, welcome to the second lesson in this comprehensive calculus course. Let's go ahead and get started. So last time we were talking about the idea of finding rates of change on nonlinear functions. So for example, I have this one is difficult. So I've got my coordinate system here, the XY plane. And I have a nonlinear function. And I'm interested in finding the rate of change of this function at some particular interval. So on some particular interval, let's say, for example, from A to B. Now, what we can do is we can, of course, construct a secant line that passes through A and B. And then we can go ahead and find the slope of that secant line. And that will give us the average rate of change of our function. So we'll call this function f of x. So it'll give us the average rate of change of our function on this interval from A to B. And so we can define the average rate of change, I'm just going to call it average ROC, to be equal to the gradient of the secant line. So we know the gradient is delta y over delta x, which in this case could become f of b minus f of a divided by b minus a. Now, we also talked about what if we want to find the slope of the function f of x at one particular point. So for example, if I'm interested in finding the gradient of the slope of the curve f of x at the point a comma f of a, then how could I do that? Well, it turns out that we can create a unique tangent line that's going to be passing through this point, and that will exactly coincide with the function so that the function and the tangent line are indistinguishable at this point, so that the slope of the tangent line at that point, well, the slope of the tangent line will be the same everywhere, but the slope of the tangent line will be the slope of the function at that particular point. And we were calling that the instantaneous rate of change. So let me just use an abbreviation, IROC. So the instantaneous rate of change. And how do we do that? We let the distance between the 2 points get closer and closer together. So we used some idea called the limit. So in this case, it would be as B gets closer to A, you find this ratio like this, and that would give us the instantaneous rate of change at that point. And so this idea emerges of the limit concept. And what does the limit do? It allows us to calculate the value of this type of a ratio. So in other words, if we let B get close to A, eventually B minus A would be 0. But we can't have B minus A equal to 0. And so what we need to do is incrementally let B get close to A until it's infinitely close. Okay. And later on, we'll talk about, things that are infinitely small. We call those differentials. So in this lesson, we're going to start by defining this operation that we used, wherein we let the distance between B and A get infinitely close to 0, but not exactly 0, so that we could go ahead and calculate the slope of that tangent line at that specific point. Okay, so first of all, let's give a definition here. So I think it's this colorful definition. So here's my definition. It goes like this. We can say that, or we write, what is it? Okay, try to see. So we write like this. The limit Reach out. Okay, maybe it's better. Yeah, that's much better. Okay, so the limit as x goes to, we'll say a of f of x equals L. Okay, and we say like this, that this is called the limit of f of x, our function f of x, as x approaches a, but never actually equals a. Okay, in some cases, we'll talk about that. As x approaches a, equals L. So here we've got L is some value, and in fact, L could be finite or infinite, but right now we'll just assume that it's finite. Okay, equals L. If we can get arbitrarily close, so in other words, if we can, let me say make, if we can make f of x arbitrarily, so that means, as close as we like, okay, arbitrarily, if we can, forgot to write make, if we can make f of x arbitrarily close to L as x gets close to a. So you could say as x gets sufficiently close to, but not equal to, a, and we do have to specify on either side of a. Okay, so that, it seems like a lot, but let me show you what it means with the picture. So what does it look like? It looks like this. So I've got my graph here. I'm on my XY plane. And we've got some function here. Let's use this one. Let's use this one. Yeah. So I've got some function here. Okay. And then I've got some value here. We'll call it A. And then what we're doing is we're seeing, okay, here's A. Here is f of A. And actually, in fact, this is also, this f of A would also be, actually, it's a little bit high. Make it lower. Okay, so here's f of A. And so the idea is like, no matter how close I get here, so as I'm getting close to A from this side, so here's x is getting close to A over here. And also we can get x close to A from this side as well. So as we do that, this side is also getting closer and closer. So f of x from here is getting closer, and this f of x over here is getting closer and closer to f of A, which is this point here. Okay, so in this case, we would say that this is L, right? This is our L, because no matter how close we get to this A, we can get closer and closer to this point right here, this f of A. All right, so then now let me give you an example where it will really bring out what's so useful about this limit. And that is the case where we've got a function like this one. So let's see. We've got this function here, and let's see, I want to make the function like this one. So I'm going to go like this. Okay, so this function is the function f of x is equal to x minus 1 over x squared minus 1. Okay, so here you can see that for this function, there's some kind of a problem here for as far as our domain goes. And I'll show you what I mean. Because if x is equal to 1 or negative 1, actually, is it? Yeah. So if x is equal to 1 or negative 1, and let's just say we're only interested in the positive values. Okay, so we'll just stop it right there. And then I'll just explain this more. So I'm just interested in for x greater than or equal to 0. So if x equals 0, you can see that this point would be, we'd get 1 here, 0 and 1. But if x equals to 1, well, that's not a possibility. Let me try to draw it a bit better here. Oh, no, that's not working out. Hold on. Okay, great. So if we can't have x equal to 1, of course, because if we have x equal to 1, then our denominator and our numerator would both be equal to 0. So actually, you can see that this function is not defined at this point, x equals to 1, right? And let's see, actually, let me make it a little more like big. All right. So this function will look something like this. Now that's much better. Okay. And then of course here we have a hole because there's no, oops. That's what I want to do. Here we have a hole because it's not defined at 1, right? Because if it's equal to 1, then we get 0 in our denominator. Okay, so then the question becomes, what's the limit as x goes to 1? So that's where this limit really comes in handy, because you can see that the function doesn't have a value at 1. It's not defined for 1, but it still certainly can have a limit. So what we can do is we can look at what is the limit as x goes to 1 for our function x minus 1 over x squared minus 1. And in fact, for this function, we could just look at it here. And if we know what this value is, we can see that as x gets closer and closer to 1 from both sides, if we go this way along the y-axis, if we were like walking along this graph, as x gets closer to 1, we're getting closer over here to 1/2. So this would actually be 1/2. And from the left side as well, if x is getting closer to 1, then as you go down this graph, we're getting closer and closer to 1/2 in this direction. And it's not hard to see that on a graph, right? So even though we don't have the function value at 1, we can see that actually as x approaches 1, we're getting closer and closer to 1/2 on the y-axis. Okay, so as the x goes to 1, the function's value has a limiting value of 1/2. And it's approaching from the left side and the right side to that value. And in fact, if it did not do that, then we would not be able to say that it has a limit. Okay, so we can see graphically by examining the graph what the limit of a function should be, right? In this case, but we can also So the graphical inspection or the graphical analysis can help us to determine what should the limit of the function be. We can also use algebra, and this is the way it's usually done, is through algebraic evaluation. And here, when we're doing an algebraic evaluation, if we want to take the limit of this function, or any function for that matter, if we have the case where we have a 0 in the denominator, then what we need to do simply is to try to factor this, or another way of algebraic manipulation, so that the 0 is no longer in the denominator. So in this case, you can probably see that in the denominator, we have a difference of 2 squares. And so this becomes x minus 1 divided by x minus 1 times x plus 1. And so we can divide our x minus 1, and we're left with this, the limit as x goes to 1 of 1 over x plus 1. And now, once you no longer have 0 in the denominator, there's no problem for x to go to 1, to actually be equal to 1, because then we're not causing the problem of division by 0. So now that we no longer have that problem with division by 0, we can go ahead and plug in x for 1, and we're going to get 1 over 1 plus 1, which is, of course, 1/2. And so that is the limiting value of our function. All right. So right now I've shown you 2 different ways to examine the limit. One of them was graphical analysis. The other was an algebraic analysis. And let me show you another way that we can do it, which is using a table of data. So, but before I do that, actually, let me just mention one other fact here, one other theorem. So in this case, this function has a limit, and we saw that the limit was equal to 1/2 as x got close to 1. But what if you have a function that looks like this? So let me draw another one then. So suppose I've got this function. Let's say it's like this, and this function will, let's say, will go like this one, and then I'll make a 1. And so I've got a function that's a piecewise function, and so it's going to kind of look like this. And then here, we'll just kind of have a little parabola. Okay, so I'm going to call this point A. And so this point would be f of A. So this point would be f of A. And you can see here what I've tried to do in this picture is, let me try to make it a bit more clear. I've tried to make a hole here, meaning that at this location, the function is not defined. Okay. All right, so there's a hole there, right? So our function is, it's a piecewise function, and it's defined to be some kind of a straight line. Okay, so we'll just say on this side, so we'll say, let me say it like this actually. So it's mx plus b. So this line, whatever this line is, right? For x greater than a. And then down here, we've got this sort of half of a parabola, which could be, it's going back up. So we'll just assume it's a parabola. Then we've got some sort of ax squared for x less than or equal to a. Okay. So, I mean, the particulars of the formula aren't really that important. I just want it to be pretty general here. And then you can, use more specific cases later on. But then the question arises, what is the limit of this function as x goes to a for f of x. Okay, and so the problem is here that you can see there's not an agreement at a, because we have two pieces of the function. We've got a piecewise function where the piece is split on a. And so in order to determine the limit of this function, we have to check the left side of a and the right side of a. And so this gives rise to the idea of a left-sided limit and a right-side limit. So we do in fact have those two definitions. All right, so for a first definition, we'll do the left-side limit. We say that the limit as x goes to c, and we use a little minus sign here to mean from the left of f of x equals L. Okay, so this is our left side limit for x less than c. Okay, so this would be our left side limit, and the main thing here to notice is this notation, but I'm using this minus sign, so we use this minus sign right here, and also that x is on the left side of c. So this is the definition of a left side limit. Okay, and so here in this case, our left side limit for this function, so let me just erase this now. So for this function, our left side limit would be, so if we want to take the limit as x goes to a from the left side of f of x, well, in this case, you can see that as we go, as the x gets closer to a, you can imagine you're like walking along this graph, getting closer and closer to this point here, for which the function is defined, although it's not relevant, and we can see that the limit is f of here. Okay, but here, this is not f of a, right? This is f of a plus some kind of a distance here, so we'll just call it f of a plus h, where h is the distance between a and this point, whatever it is, right? And so if we look at the right-hand side, so the right-hand side, it's the same definition as the right-hand limit, except now we're going to use this plus sign. So if we look at the limit from the right side, we see that we don't get f of a, we get f of a plus this distance up here of h. So in other words, if I'm a little person walking along this graph, and as I'm getting closer to a, I'm getting closer to this y value. All right, and so what we can see here is that these two things are not equal, right? F of a is not equal to f of a plus h because it's h units away, h positive, this is positive value, right? So they're not equal. And so what it means then is that we have to say this, since the left-hand limit and the right-hand limits are not the same, since the left-hand limit and the right-hand limit are not the same, and what does it mean? Then this limit as x goes to a for f of x does not exist. And usually we'll use an abbreviation, and we might even write down something like this. We'll say the limit as x goes to a for f of x, you might even say equals d and e. Okay, so this just means it doesn't exist. And the reason it doesn't exist is because the left side and the right side don't match. They're not the same. Okay, so if the left side limit and the right side limit are not equal, then we say that the limit fails to exist. Okay, so that's something we need to make sure to take a note of here. Okay, so now we talk about the definition of a limit and what it means that we can get arbitrarily close to some value, even if it's the case that the function is not defined for that value, as we saw here. Here we could see that this function is not defined at x equals 1, but we can get arbitrarily close to 1, but never equal to 1. And as we're getting arbitrarily close to 1 on the x-axis, what's happening on the y-axis is that we're getting arbitrarily close to 1/2 on both sides. And so since that's the case, we see that the limit has to be 1/2. And then we could also show that algebraically. So we could see it from our graphical analysis, and we could see it algebraically by using methods like factoring and so forth. And we'll see there are many different tricks that you'll see in fact that you'll learn so that you can factor, so that you can take the limits, evaluate limits of different types of functions, different functions of different types. Okay, and then here we did a graphical analysis to show that there exists a left side limit, there exists a right side limit. But if those two are not equal, then we say that the limit of the function at that point, at that location A, does not exist. Okay. So now we've seen the definition of limit, we've seen left side limit, we've seen right side limit. So there are 4 ways in general to evaluate limits. Okay, the first one is what, like we just saw a moment ago, there's the graphical method, where we're just looking at the graph and we're making note of left side limit, right side limit, seeing if they are the same or if they're not the same. And then just looking at the graph. The second way, which is the most often used way, is the algebraic method. And this just involves factoring or using algebraic manipulation. Usually, we're trying to remove some term in the denominator that will end up being equal to 0 if we let the value go toward, if we let x go to a in that sense. The next way is with the table or data, and that's what we're going to show you next. And then the last way is with the theorem called the squeeze theorem, which we're going to look at as well. Okay, so we've got 4 different ways that we usually look at different, look at how to evaluate limits. Now, the next one I want to show you is using a table. All right, and oops, okay, and so the example I want to use is, so graphical, no, I meant not graphical. Oops. Using a table or using some data. All right, so we're going to say evaluate the limit. Using data. Okay, so suppose we've got this function and write down the function. So my function is going to be f of x is equal to e to the power of x minus 1 divided by x. Okay, and now I chose this function because it's very difficult to factor it or do some kind of algebra with it, although you can do it, but it's just a little difficult. And what we're interested in is we want to find the limit as x goes to 0 for this particular function. So let me try to write it down. So I'm going to use the limit as x goes to 0 over e to the x minus 1 over x. Now, if you try to plug in 0, you're going to get e to the 0 minus 1 over 0. So already we can't have 0 in the denominator, but then we're going to get 1 minus 1 over 0 to 0 over 0. And this is called indeterminate. which later on we'll look at a shortcut for when we have limits that are indeterminate. But right now, we don't have any tools to deal with indeterminate situation when we're taking the limit. And so what we're going to do instead is we're going to use technology, and we're going to look at a table of data. So then what I'll do is grab my technology. And what we want to do is we want to look at the limit as x goes to 0, which means that we have to examine the left side limit and the right side limit. So let me change the screen share. And I'm going to be back. I'm going to be over here on my TI-84 calculator. Okay, so here I'm going to enter the function here. So I have, what is it? E to the power of x minus 1. And then down here, I have x. Okay, so there's my function. And now what I want to do is go out here and just call it like this. Okay, so there's my function here. So what I'm going to do first is go on the left side of 0. So I'm interested in the limit as x approaches 0. So I'm just going to start here on the left side of 0 at negative 0.1, or just negative 0.1. Okay. And we'll see what we get. We get 0.95. Okay, so let's do it again, except we're going to get closer to 0 by putting a 0 here. So 0, 1. And then we click enter. Okay, now we're getting, so we have 9.5 first, now we have 9.95. Okay, let's do it again. And we'll put a second 0. And again, and so now you can see what's happening. First there was 1, 9, now there are 2, now there are 3. Okay, so what's happening to this number as x gets closer to 0 from the left? What's happening to the y value? That's what we're interested in. So let's do another 0 here. And what do you know? We've got more 9s. And I could continue doing this. How many times could I do it? I could do it. I could do this infinitely many times. Actually, I couldn't do it infinitely many times because I might not live very long past, like 70 or 80 if I'm lucky, right? But I could keep putting zeros like this until the time I die, and I will just keep getting closer and closer and closer because these numbers are, they have infinite number of digits. It's amazing. So anyways, that's sort of an abstract point, but it is quite amazing. And it's the reason why we're able to use this process is because I can continue to do this. And now you can see I've added another 0 and I have another 9. So it's safe to say at this point that the left side limit as we approach 0 it's getting closer and closer to 1, isn't it? Every time we put another 0, we get another 9. So we can write that down over here. Maybe. So let's go ahead and write that down. There we go. Yeah, okay. So in order to take this limit, right, we have to take the left side limit and the right side limit. And just in case it's not clear why we have to do that, it's because of the fact that if we try to plug in 0, we will actually not be able to, we get that indeterminate form. Okay. So the left side limit, so the limit as x goes to 0 from the left with the little minus sign there of e to the x minus 1 over x is equal to 1. Okay, so when we say that it's equal to 1, we mean the limit is equal to 1. The limit is equal to 1. So can it be equal to 1 even though we never actually arrive at 1? Yes, because we're saying that the the limiting value is 1. I'm having a hard time drawing a 1. Okay, so if we keep getting closer and closer, if I keep putting zeros and zeros and zeros, it will never go past 1, right? And actually, it will never be 1. I mean, if you have like 3,000 nines after a decimal and then a 5, you might as well just consider that number 1, right? So from a practical standpoint, so now we need to check the limit as x goes to 0 from the right-hand side and see what we get. All right, so let's go back over here to the calculator. To the share. Okay, so now let me just clear the screen. And we'll start over on the right-hand side. So what I'm going to do, I'm going to do the same thing as before, except this time, I mean, I'm not going to use negative sign. So now I'm going to take, so remember, I just want to remind you, this y1, this is where I stored my function. Okay, so that's why I'm using y1 over here. All right, so I'm going to put 0.1 here. Click enter. Okay, there's our first value. Let's do it again. Now we're going to put a 0 between the decimal point and 1. Okay, and look what's happening already. Well, I mean, I've done this like so many times, but maybe you can start to see the pattern. It's a pretty evident pattern, I think. 1 0, 2 zeros, 3 zeros, right? And that's going to just continue on like this. And so what's happening is exactly the fact of as we're getting closer to 0, the y value, so that's the x value, the x input value is getting closer and closer to 0. The output value, the y value, is getting closer and closer to 1. Let's do one more. And so the limiting value is 1 as x approaches 0 from the right-hand side. All right, so now let's go back over here to our pad. So we've seen that the left side limit is equal to 1, and the right-hand limit is also equal to 1. So that means that the limit exists, and the limit as x goes to 0 exists, and we know that it's equal to 1. Okay, and later on we'll show this, we'll prove this in an algebraic way later on. But right now we have this fact. I forgot to write down. Right now we have this fact that we can use, that the limit as x goes to 0 of e to the x minus 1 over x is equal to 1. And this is going to be an important limit that we'll see later on when we start deriving differentiation formulas for the different types of functions. Okay, so next up, let me just do a few examples here, perhaps, and then we'll call it quits. And then in the next session, we'll go over the squeeze theorem. So let me grab one thing here. Maybe I can just do like this. So we've seen how we can investigate limits at various different points to try to see if we can investigate functions to see if the limit exists at some particular point or not. I always forget how to make this bigger. I know you can make it bigger. I can spin it around in circles. That's not really what I want to do. Ah, perfect. Okay. Yeah, there we go. All right, so now let me just, there we go. So here, let's just do a couple of exercises here. So the first question then would be, what's the limit as x goes to -1 for our function f of x here? Okay, so here's our function f of x, right? And let's just see if I can. So it's got a lot of different pieces to it. So how can we find the limit as x goes to -1 of this function? Well, we have to look at the left-hand side. So the left-hand side. So what's happening as x gets close to -1? What's happening to the y value here? And we can see here that I can write this down, that as x goes to -1 from the left for f of x, my limit is 0. Great. And now we'll go over here to the right-hand side. As we're getting closer to -1, what's happening here? If I'm walking along this line, I'm getting closer to 1. Actually, I'm going to stay at 1, right? Because it's a flat line right there. So on the right-hand side, the limit as x goes to -1 from the right side. Oh, it doesn't look like it. The limit as x goes to -1 from the right-hand side of our function is equal to 1. So right away, we can see that these two things are not equal. And so what does it mean? It means that the limit as x goes to -1 for this function does not exist. Now, there is a left side limit and there is a right side limit. And that's important to note because later on, we'll talk about left and right continuity, or left side and right side continuity, so and things like this. Okay, but just know that you can still have a left side limit, you can still have a right side limit. In fact, you have to, but that doesn't. But if they're not the same, then you don't have a limit in general at that location. Okay, so if the left side limit does not equal the right side limit, we say the limit does not exist. Okay, great. Now let's look at the next location. Let's just say we're interested in 2. So I want to take the limit as x goes to 2 for f of x. Okay, so that means we need to take the left side limit. So the limit as x goes to 2 from the left of f of x, what is that going to be? Well, from the left, I'm going along this direction, getting closer to 2. My y value is getting closer to 1. And also you can see that the same is going to be true for the right-hand side. So it means that the limit as x goes to 2 from the right for f of x is also 1. And so we get that the limit as x goes to 2 for f of x is equal to 2. Now, I'm sorry, 1, not 2. It's equal to 1. And there's going to be a special condition that we can think about here. And you can see it now. There's a special condition, a special property of functions whose limits are equal to the value of the functions at those particular points. Okay, so you can see what happens when we have a limit, but the function doesn't have a value, right? You can see here we have a function that has a limit, but the function is not defined at the location where the limit exists, right? And that's fine. But you can see that that is indicative of the fact that there's a hole right there. And then in these other situations where we have the left side and the right side are not equal, then that indicates that there's a break in our function, so that it's not smooth curve. There's a break. Okay, and that's going to become really important when we finish discussing the limits and squeeze theorem. And I'm going to give you one more example before I sign off here, and that is one more way to solve a limit algebraically. So let me just do 3 real quick examples. So, and then later on we're going to talk about the properties of limits. But first, I'll just give you a few quick examples. So let's say I want to take the limit as x goes to 2 for the function x squared. Well, this thing's a polynomial, right? And there's a certain class of functions, polynomials, rational functions, trigonometric functions, where if the value that x is approaching is in the domain of the function, we can use something called the direct substitution property, right? So here, I'm just going to plug this in, and I'm going to get 4, okay? So this is like, a special type of function where the limit of the function is actually equal to the value of the function. Let me give you another example. let's say I have the limit as x goes to 16, and I've got 4 minus the square root of x divided by 16x minus x squared. Okay, so here there's a lot of problems here. One of them is if I plug in 16, I will get 4 minus 4, which will be 0, divided by 16 squared minus 16 squared. So 256 minus 256. So I will get indeterminate form if I plug in 16. And also there's a problem here where I've got a square root here. Okay. So one thing you can remember is something called the difference of two squares. So if I have a minus b times a plus b, what do I get? I get a squared minus b squared. And you might remember something called a conjugate. So anytime you have a square root, when you're taking a limit, it's a good idea to try to multiply this by the conjugate. Because if I try to factor this thing, there might be some way I can factor out this x and then, factor out the square root here. But it might not work out very well. So what we want to do here is try to multiply by the conjugate. So, and this is just one of those tricks that somebody has to show you. Okay? It's not something you would naturally think about. Maybe you would. This depends on your level of training. Okay, so here I've got the conjugate divided by itself of 4 minus square root of x, and I'm going to multiply that. Now, whenever you're multiplying things, when you're evaluating limits, you never want to multiply the bottom one out. You always just write those next to each other. So that's what we're going to do here. We're just going to make some brackets. And I'm not going to multiply these out, just like this. But I am going to multiply the top piece because I want to remove this square root of x so that perhaps I could factor out one of these x's down here. So I'm going to take, well, I've got a minus b times a plus b here, right? So that means I should get a squared minus b squared. So a is 4, so I'm going to get 16 minus b squared will be just x. So I'm going to get 16 minus x here. All right, now it's looking good. And so the next thing we're going to do is we're going to let x go to 16, 16 minus x. And then down here, we'll factor out this x. So I've got x times 16 minus x. That works out very nicely. And this is, you can see the reason why we don't want to multiply the bottom, because this will factor out nicely in most cases. So we can divide this now, and we're going to get the limit as x goes to 16 of 1 divided by x times 4 plus root x. Okay, and now we can plug in the 16 because it will be, it will not create the division by 0. And so when I do that, I'm going to get 1 over 16 times 4 plus the square root of 16, which will give me 1 over 16 times 8, which is going to be 1 over 250, no, 1 over 128. Okay, so then I can write down like this. Limit as x goes to 16, 4 minus the square root of x divided by 16x minus x squared is equal to 1 over 128. Okay, and so that's where I'm going to stop today. And then next time, when we start, we're going to look at the properties of limits. And I mentioned before, so I'm going to formally list these out, formally enumerate all of these properties, because it's really important to know these, because everything else that we're going to do is a limit of some sort. A derivative is a limit, an integral is a limit, and so they inherit the properties of the limit operation. And so this is where we'll start next time. We'll look at those properties of limits. We'll look at more ways to evaluate them algebraically. I'm going to show you all of the classical uh, classical tips and tricks that you would have to have somebody show you. And then we'll move on to the squeeze theorem. Okay, that's it for now. I hope that helps. Thanks for watching. Please let me know if you have any questions, comments, suggestions, or if you notice a mistake, in my understanding. Okay, thanks so much.